Hello everyone. I welcome you all to the lecture 2 of week 4. In this lecture, we will be studying various displacement, position, and proximity sensors. Well, my friends, the outline of this lecture is as follows. We will be learning various sensors such as strain gauge based sensor, capacitive elements, LVDT, that is linear variable differential transformer, eddy current based sensor, and inductive proximity switch. We will learn the principle of operation of these sensors, their construction details, and we will study the applications of these sensors in the automation industry. So let us begin. The next important displacement sensor is strain gauge element sensor. It works on the principle of change in resistance when we are giving tension or compression to a mechanical element. On your screen you can see a simple arrangement of a strain gauge element. So, it has a foil and that foil has two terminals and we are measuring resistance across these two terminals. This foil is attached to the mechanical element of which we want to measure the strain. When there is a tension in the foil, then the resistance of that foil or the resistance of that mechanical element will increase, and when there is a compression, then the resistance will decrease. So, it works based upon the principle of electrical resistance and it is particularly measuring the mechanical strain inside the work parts or the body parts of automated system. Strain gauge sensors are available either in metal wire form or metal foil strip form. The strain gauges are also made up of semiconductor material. So, the advantage of semiconductor material that it has high gauge factor. We will see the meaning of the gauge factor. So, as I said, the resistance is directly proportional to the strain. In strain gauge element, the ratio of change in resistance of the mechanical element to its original resistance is directly proportional to the strain that is developed in the mechanical element. So, I can write the change in resistance due to the strain to the original resistance is directly proportional to the strain, and the constant of proportionality is called as the gauge factor. So, in general the gauge factor is about 2 to 4 and it is decided by conducting the actual experiments in the laboratory. This is called the calibration process. In the calibration process, we are computing the gauge factor for known displacement, for known strain inside the mechanical element. So, for a known strain, we are computing delta R, that is change in resistance inside the coil or the foil, and accordingly we are computing the G. So, in general a gauge factor of 2 to 4 is noticed for the variety of mechanical elements. The most common material which is used as the strain gauge material is Constantan alloy. It has copper and nickel in the proportion of 55% of copper and 45% of nickel. Two more pictures are there on your screen. In the first picture you can see a thin foil, and on the thin foil a wire is wound, it is attached. In the second picture we are having a metal foil. So, the foil is again instead of a wire, it is a foil is nothing but a thin layer of the metal which is cut as per the required dimension. This foil is in continuous mode that you can see, and it has the connection leads. So, as I mentioned, the foils are also made up of Constantan alloy, and the foils are of size of a postage stamp, and we are pasting these posted stamp like strain gauges on the mechanical element of which we want to measure the strain. The metal foils are attached to the plastic, and that we call the bonding to the plastic by using epoxy material or glass fiber reinforced epoxy material. And this entire strip which is having the metal foil or the metal wire and the plastic material is secured to the workpiece by using again a epoxy or a special material, that is cyanoacrylate cement Eastman of number 910 SL. So, these are the materials which are helping us to paste the postage stamp size strain gauge elements on the machine tools or on the product of which we want to measure the strain or the displacement. Well, strain gauge element is providing us the passive output. So, passive output, as we have seen, it is producing the change in resistance. But for microprocessor processing or for microprocessor, we need the active element, we need the voltage, change in voltage, a pulse of voltage, that is the digital signal that is useful for the microprocessor. So, for that purpose we have to convert the resistance change into voltage change. So, to carry out this operation we are using Wheatstone's resistance bridge. A typical arrangement of the Wheatstone resistance bridge is shown on your screen. So, in this arrangement we are using 4 resistors R1, R2, R3 and Rx. Supply voltage is applied across a bridge of these 4 resistors, and output voltage is measured across the 2 connections A and B. The values of these 4 resistors are chosen in such a way that the V0, that is output voltage, should be 0. So, when the output voltage is 0, then we are saying that the bridge is in balanced condition. So, to have output voltage is equal to 0 volt, if you try to get the correlation between these resistor values, you will find that when we are having R2 divided by R1 is equal to Rx divided by R3. So, to get 0 voltage we are choosing R2, R1, R3 and Rx. Now, in the application of Wheatstone resistance bridge, we are attaching this Rx to our strain gauge leads. So, let us attach our strain gauge at Rx. So, whatever the output that is coming out from the strain gauge is the Rx value. So, for no load condition, some resistance is providing by, for no load condition the strain gauge is providing certain resistance, that is Rx. So, for Rx we are choosing the value of R1, R2, R3 such that this equation satisfies. But when this strain gauge is in action, when there is tension in the strain gauge, so the resistance of Rx is getting increased. There is change in Rx value due to the mechanical movement which is occurring, that is strain that is occurring. So, as Rx is increasing or it is changing, so we are getting certain output at the VO. So, the output at VO will not be 0 volts, it would be a non-zero output at this. So, to make it 0, we have to change the resistance of one of the other resistors which are R1, R2 or R3. So, we have to change resistance of either of R1 or R2 or R3. So, we can choose any resistor here. So, let us consider if we have chosen how much should be the change in R1 so that we can achieve our condition that V output is 0 volts. So, that means we have to carry out the resistance change, it may be plus or minus. We have to add a resistance of plus or minus delta R into R1 so that we are getting this condition. So, the change in resistance in R1 resistor is the indicator of the strain. So, the change in resistance at R1 to get output voltage is equal to 0 is indicating the strain inside the strain gauge, strain value. So, in laboratory for known value of strain values, we can easily get the delta R1, and in this way we can calibrate the strain gauges. So, when we attach the Wheatstone resistance bridge, a simple strain gauge element sensor will be converted into a transducer. Some more pictures are there in front of you which will clear your idea of the strain gauge. So, here you can see the strain sensitive pattern and the terminals of a typical strain gauge. Now, the figure B shows when the tension is there, the cross section area is getting narrowed and the resistance is increasing. So, the higher resistance are indicated here. When compression is occurring along the length, then we are getting thickening of the area, the cross section area is thickening and the resistance will decrease. So, we are getting lower resistance. So, the strain gauges are effective when there is a the longitudinal strain along the length. When the strain is occurring, then the strain gauges are working. For the lateral application of the strain, these are ineffective. So, some information is there in front of you. Basically, the strain gauges are useful for measurement of displacement from 1 to 30 mm. So, 30 mm is a very decent significant number. However, they do have a non-linearity error of 1% and it is basically due to the temperature, because when the temperature is high, when the harsh conditions are there, then the temperature will affect the material properties of the metal foil or the metal, and that may lead to errors in the measurement of the strains. So, these type of strips are attached to cantilevers, pipes, U-shaped elements, and accordingly the strains are measured. Now, on your screen you can see we can measure the vibration, how the vibrations are measured. If suppose we are applying a repetitive load at the cantilever beam here, the load is applied intermittently, then what is happening, the strain gauges which are pasted on the top surface, they are experiencing tension due to the tension in the fibers of the top surface, while the fibers which are there on the bottom surface of the cantilever are experiencing compression. So, we are getting increase in resistance values of the top strain gauges and decrease in the resistance values of the bottom strain gauges. So, by monitoring the periodicity of, or by measuring the periodicity of the signals which are getting from the strain gauges for its increase and decrease, we can easily monitor or record or measure the vibrations value. Second is a pipe, a thick pipe. So, when we apply a load over a thick pipe, again we can find out the deformation in the thick pipe. On its outer surface, here we can notice the tension, so increase in resistance, and the inside strain gauges are measuring the compression. The third is a U-shaped channel which may be part of your mechanical system. Some applications are there in front of you. Basically, strain gauges are widely used in experimental stress analysis. So, those who are carrying out MTech or PhD projects in mechanical manufacturing, basically in experimental mode. So, for stress analysis and for diagnosis of machine tools, strain gauges are widely used, particularly to measure the forces. Moreover, for fatigue analysis, fatigue testing, stress analysis, vibration measurement, as I mentioned just now, torque measurement, bending and deflection measurement, the strain gauges are used. In machine tools, particularly in hydraulic and pneumatic presses, since we are applying more pressure, more hydraulic pressure or more pneumatic pressure on the pipes or the elements of these systems, there may be strain, there may be deformation in these mechanical elements. To monitor the deformation of these elements, it is very essential to paste certain strain gauges and get the output from them. Safety in automotives, a very important feature of today's automotive is the airbags which are protecting during the collision. So, these bags are operated based upon the strain gauges. Impact sensors in aerospace vehicles, these are also an important application. The next sensor is capacitive element sensor. Its advantage is that it is a non-contact type of sensor and it is used to monitor the displacement. So, when two charged plates are in the vicinity of, when two charged plates are closer to each other, then the capacitance developed in between these two charged plates is directly proportional to their area of overlap and it is inversely proportional to the distance between these two plates. So, the constant of proportionalities are called as the relative permittivity of dielectric between the plates and the permittivity of free space. So, what is the meaning of permittivity? So, permittivity basically relates to the material's ability to transmit an electrical field. We are having two charge plates and there is a material or there is a medium in between these two charge plates. The ability of this medium to permit an electrical field is nothing but the permittivity. So, here we are considering sigma r is the relative permittivity of the dielectric medium between the plates and it is considered as 1 for vacuum, whereas sigma O is the permittivity of the free space and the value is shown on your screen. So, this useful principle can be utilized for measurement of the displacement in our domain, that is manufacturing automation. How, that we will see now. So, on your screen you can see configuration, there is a top plate and there is a bottom plate and these two plates are separated by a distance d. There is a overlap of A between these two plates. So, when this separation is increased, so d plus delta x, if I am increasing it by a value delta x, then the capacitance is changing. So, we are getting C minus delta C. So, if we are increasing the overlap area or we are decreasing the overlap area, that is also affecting on the capacitance. So, here you can see the area in this case is reduced. So, here I am reducing the area by an amount delta A minus delta A will also reduce the capacitance. So, let us consider one of these plates is attached to the mechanical element in our domain, then by changing the separation or by changing the overlap area, we can easily measure the change in capacitance. Of course, change in capacitance is the passive output that we are getting. We have to convert the change in capacitance into the change in voltage value. The third case in capacitive element may be the movement of the dielectric medium itself. So, as we are moving the dielectric medium as well, we are getting the change in capacitance value. So, the capacitance is function of separation distance, area of overlap and movement of dielectric medium. So, this change in capacitance further utilized to get the displacement. Right. So, now you can see how exactly we can use the capacitive element sensor in the practical domain. So, for that purpose we are taking 3 plates, plate number 1, plate number 2 and plate number 3. Now, the second plate is attached to the element of which we need to measure the displacement. So, in this figure B, you can see the middle plate has been moved in an upward direction, which is closer to the top plate. So, when we are moving it towards upward direction, there is increase in separation distance between plate number 2 and plate number 3, and there is decrease in separation distance between plate 1 and plate 2. So, as the principle of the capacitive element sensor is suggesting, when the separation distance is decreasing, there is increase in the capacitance between plate 1 and plate 2, and there is decrease in capacitance between plate 2 and plate 3. Or somebody will use the movement of the plate number 2 in a lateral way. So, when plate is moving in a lateral way, you can see the area of overlap is getting changed. In this case, the complete area of plate 2 is being overlapped by plate 1 and plate 3. However, in this figure you can see there is only half area is being overlapped with plate 1 and plate 3. So, naturally there is a decrease in capacitance. So, the decrease in capacitance can directly be calibrated to the displacement. The capacitive element sensors are widely used as proximity sensors. So, in this case we are using a simple arrangement. So, we are using a coaxial cable and there is a guard ring. The guard ring is protecting the coaxial cable. At the end of the coaxial cable, we are attaching a plate. This is the charge plate. So, when this charge plate comes closer to object, which is earth object, which is connected to the earth, then the capacitance between these two objects will change, and that triggers a signal, and that signal may be utilized to take the action. Consider these kind of sensors are used as a proximity for automated guided vehicles. They are mounted on the front side of the automated guided vehicles. When this plate will come in the proximity or vicinity to an object, it produces a signal and that signal will stop that vehicle. A typical industrial construction of these capacitive sensors are seen on your screen. This is the sensing area, which is small. However, the sensing area is guarded by the guard area, and the guard construction and the sensing construction are enclosed in a body. Capacitive proximity switches are working with target. Only condition is that the target should be grounded. When these capacitive sensors are coming closer to the target, it producing the signals. So, here you can see and charge is applied to the coaxial cable, and when they are coming closer to a target, then there is a change in capacitance which will be useful to generate the signal. So, what are the applications of capacitive element sensor? They are used to monitor the feed in hoppers. So, hoppers are nothing but a material handling device through which we are feeding the commodities inside automated system. Let us consider a injection molding. The hopper is nothing but a conical flask which is mounted on the injection molding machine, through which we are feeding the granules of the polymers inside the mold area. The machine tools or the machineries which are used in automation, we need to continuously lubricate them. So, for that purpose the grease is being used, and to monitor the grease level we are using the capacitive element sensor. Then liquid level also can be monitored using capacitive element sensor. Capacitive element sensors are very useful for metrology applications. So, when we want to measure the shape errors in the part which is being produced, then the capacitive element sensors are useful. Let us consider a cylindrical part that to be manufactured by using the casting. However, due to manufacturing errors, we have not achieved a proper shape of the casting. You may consider that there is a bulge, the casted component. So, when such component is moving over the conveyor, so this bulge is easily sensed by the capacitive element sensor. So, let us consider if these kind of atoms are moving over the conveyor continuously, the capacitive element sensors are mounted over here. When these elements are moving, there is a constant gap or the known gap. When there is a abnormality or non-uniformity or error in the shape, so this known gap will be changed, and that known gap will trigger signal inside this capacitive element. So, that will be useful for us to monitor the product shapes during the manufacturing operation. Moreover, they are used to monitor the rotation of the spindle in various machine tools, that is the health monitoring of the machine tools such as grinders, lathes, milling machines. Well, the next important and useful transducer which is used in automation, that is linear variable differential transformer, and it is widely known as LVDT. The short form LVDT is very popular. These kind of sensors are used to measure the displacement between plus or minus 2 mm to say about 400 millimeters. These sensors has non-linearity error of 0.25%. Well, the principle of operation is very simple. In linear variable differential transformer, we are using 3 coils. The first coil is the primary coil, then we are having a set of secondary coils, secondary coil number 1 and secondary coil number 2. These 3 coils have equal number of turns. We are applying constant alternating current voltage to the primary coil, and the secondary coil number 1 and secondary coil number 2 are attached or they are connected in a such a way that their output voltage difference is 0. So, there is a phase change in the connection of secondary coil number 1 and secondary coil number 2. Now, inside these coils a ferrous rod is moved. We do have a ferrous rod. When this ferrous rod has equal overlap with secondary coil number 1 and secondary coil number 2, then we are having a 0 output voltage. So, why it is happening? When we apply constant AC voltage input to the primary coil, it generates alternating magnetic field. That alternating magnetic field will generate the electromotive force in secondary coil number 1 and secondary coil number 2 through the ferrous rod. When the overlap of ferrous rod 1 in secondary coil number 1 and secondary coil number 2 is equal, then we are getting the output voltage as 0. Why it is 0? Because the secondary coil 1 and secondary coil 2 are connected in opposite direction. So, their magnitudes are same, but the signs are different opposite. Now, how the displacement is measured by using LVDT sensors? The ferrous rod which is generating the resultant EMF across the leads or the connections of secondary coil 1 and secondary coil 2, that ferrous rod is attached to the mechanical element of which we want to measure the displacement. So, as the rod displaces, so if we consider as a rod moves in a downward direction, then the overlap of ferrous rod 1 in secondary coil 1 is reduced, while the overlap in secondary coil number 2 is the same intact constant. So, as the overlap in coil 1 is reduced, the EMF generated in coil number 1 will also reduced. In this way, we are getting non-zero voltage at the output. So, this non-zero voltage at the output is the function of the displacement. So, LVDTs are again calibrated in the laboratories. For known displacement, we can get the generation of the voltages in these coils. A typical construction of LVDT which is used in the industry is shown in the next figure. You can see a set of secondary coils and a primary coil. This is the core. The core is attached to a shaft and the shaft is having a tip. The shaft is spring loaded so that we can measure the displacement, and after measuring the displacement of the tip, it will regain its original position. So, to go to its original position, the springs are used. The output will be taken through cables and further the output will be processed, signal conditioned, and then it will send to the microprocessor. Here you can see this tip is in contact with the mechanical elements. Consider we are having a plate which is connected to some mechanical element, and as there is a movement of this mechanical element, this plate will push the tip and accordingly we are getting signals in the cables. We can measure the absolute position by using the LVDT sensors. These sensors have good repeatability and reproducibility, and they are highly reliable. The construction has no contacts, so there is no friction or there is no sliding, so there is no wear and tear of its construction elements. The cores do not have contact with the coils, so that is a non-contact. Of course, the measurement mode is the contact, so these tips are to be in contact with the mechanical elements or the machineries. LVDTs are used in servo mechanisms, automated measurement of machine tools. We need to have the phase sensitive demodulator and low pass filters to know in which direction the rod is moving. Now, here the question comes, how can we say the ferrous rod moving in upward direction or the downward direction? So, for that purpose we need to use the phase sensitive demodulator, and to have a quality signal we are using low pass filters in addition to the LVDT sensors. What are various applications of the LVDT sensor? On your screen you can see a mill. The mill has two rollers and this mill is used to reduce the thickness of a metal sheet. Now, there is an arrangement here to adjust the spacing between these two rollers. So, to adjust the spacing between these two rollers, we have to mechanically move the upper roller with respect to the second roller which is at the downside. So, when we move mechanically, we have to monitor whether the movement is appropriate, whether the movement is desired. So, to monitor that movement, we are using a LVDT sensor. So, if there is more movement, if there is a excessive movement of the upper roller, that will affect the quality of the product. So, to restrict that extra movement due to the inertia of these rollers, we are using the LVDT sensors. The next example on your screen is an injection molding machine. This is used to manufacture plastic components. In injection molding machine, we do have molds, and these molds are having two parts. We are opening and closing the molds. So, we should have a precise opening and closing of the molds. So, for that purpose, we have to control its operation. The molds inertia is also very high, the molds weights are also very high. So, to have the control movements, we are using the LVDT sensors. In addition to the injection molding operation, to control the feeding and the other hydraulic and pneumatic actuators, the LVDT sensors are also used for feeding mechanisms and hydraulic pneumatic actuation. We will be looking at hydraulic and pneumatic actuation in detail in the later modules of this course. One more important application of LVDT sensors. So, these are very huge size valves which are used for controlling the direction of the fluids, the water. To control the flow of water, these huge types of valves are used. These valves openings and closing is operated by using an electric motor. When these electric motors are operating these valves, there is movement of its spools. So, when these spools are moving, we need to continuously monitor the movement of the spools to have the precise control over the valve opening and closing. So, for that purpose again we are using the LVDT sensors. So, few more applications are there in front of you. Some of the applications I have already talked to you, that is the spool position measurement or control of spool position. Then displacement feedback in hydraulic cylinders, because hydraulic cylinders are being operated by high pressurized fluid. So, based on the viscosity of the fluid, there may be chances of having over travel. So, to control the over travel, we are using LVDT sensors. LVDT sensors are having very important application to control the thickness of the tablets and pills in pharmaceutical industry to manufacture the medicinal products. To have the precise thickness, LVDT sensors are used. If the tablets or the pills do not have the precise thickness, they may be discarded. Then to automatically inspect the final dimensions of the products, these sensors are used. In friction welding process, we need to control the distance between the two metal sheets or which are to be welded. So, the precise movement of the one plate with respect to the other plate is monitored by using LVDT sensors. Then in leak detection system as well, the LVDT sensors are used, where we are continuously monitoring the fluid level. In currency bills which are dispensed at the automated teller machines, so that number of currency bills that are to be dispensed are sensed by using the LVDT sensors. The linear variable differential transformers, the lengths are quite long, and in many cases that long length linear variable differential transformers are not that convenient. There is another variation of linear variable differential transformer, and that is used to measure the angular velocity. So, here instead of having the linear variation, we are using rotary variation. The cores are rotating instead of moving in a linear way. An arrangement of RVDT, that is rotary variable differential transformer, is shown on your screen. The construction is very interesting. It has cardioid shaped magnetic material core, which you can see here. This is the cardioid shaped magnetic material. We are having a primary coil and a set of secondary coil, that is secondary coil number 1 and secondary coil number 2. The principle of operation is very similar to the LVDTs. Here, as you rotate the core, you may get difference in the overlap of the core with secondary coil number 1 and secondary coil number 2. So, due to the difference in overlap, there is non-zero voltage at the output, and that non-zero voltage is nothing but the indication of angular motion of the shaft or the pin to which it is attached. This is its the ideal position or the normal position. As you can see, there is, this is portion number 1 and portion number 2. The portion 1 and portion 2 has the equal overlap with secondary coil 1 and secondary coil 2. As the cardioid shaped magnetic core is rotating, then we may have, for example, if it is rotating, then now in this case you can see there is more overlap for the secondary coil 2 than secondary coil 1. The typical construction is shown in the second diagram. These sensors are having a linearity error of about plus or minus 0.5 percentage. The next proximity sensor is eddy current type proximity sensor, and it works on the principle of electrical impedance. Impedance is the measure of the opposition that a circuit presents to a current when voltage is applied. Consider a circuit in which the current is flowing. When the voltage is applied, that circuit will oppose the current. So, that is called as the electrical impedance. So, by using this property, a proximity sensor is designed and developed, and that is called as eddy current sensor. You can understand the working of this sensor by studying the diagram. Here you can see there is a coil which is wound over a core. An alternating current is applied to this coil, and due to that alternating current, magnetic flux is generated. So, these are the magnetic flux lines. When this alternating current carrying coil is coming in the vicinity of a conductive plate, then what happens? Eddy currents are generated. So, the AC current is applied. So, we are getting AC magnetic field. When this AC magnetic field comes in close vicinity of the metal objects, eddy currents are generated. These eddy currents will generate their own magnetic field, and that field which is generated due to the eddy currents will distort the original magnetic field, the parent magnetic field. Changing magnetic field of the coil will changes the impedance. So, what is impedance? A voltage is applied, and that is creating the opposition to flow of the current. So, that change in impedance will trigger a switch. So, in this way a conductive elements or conductive plate or conductive materials can easily be detected by this eddy current based proximity switch. What are the applications? Various applications of the eddy current proximity switches can be seen on your screen. These are used to monitor the machine tool performance. The eddy current proximity switches are very useful to continuously monitor the moving targets, and that is the vibrations. The next electrical property which is helping us to design a sensor, that is inductance, which is useful to develop a sensor. It is defined as the property of a conductor by which a change in current in the conductor creates a voltage, EMF, electromotive force, in both the conductor itself and any nearby conductors. So, the change in current is creating voltage. If we are getting the change in voltage in the conductor, it is called as self inductance, and if it is created in nearby conductors, it is called as mutual inductance. So, this useful property, electrical property, is helping us to develop inductive proximity switch. A typical construction is shown on your screen. So, here we are having the LC oscillation circuit, inductance capacitance oscillation circuit, then there is a signal evaluator and then switching amplifier. So, evaluator and amplifier are signal processing devices. So, when inductive proximity switch comes in vicinity of object of material, so it generates the alarm. So, inside this inductive proximity switches there is a coil which is wound on a core. It comes close to the mechanical object which are metallic. There is a change in inductance and that change in inductance is triggering the switch. So, as the metallic objects are coming close to the sensor, there is a change in inductance of this circuitry and that is triggering. So, basically to detect the metallic objects, the inductive proximity switches are used. Various applications are there. These are used to count the products which are moving on the conveyors, but this product should be made up of the metals. Inductive proximity switches are very widely used in security for the detection of the metal objects, arms and landmines. Fine. Let me summarize the lecture 2. In this lecture, we have seen the construction details of strain gauge based sensor, principle of operation, and the applications of these sensors. Then we have seen the capacitive element sensors, LVDTs, that is linear variable differential transformer, a very useful sensor in the automation industry, ED current based sensor, and inductive proximity switch. Well, my friends, in the next lecture, that is lecture 3 of week 4, we will be learning a variety of other sensors such as optical encoders, electric connection based switches, pneumatic sensors, and Hall effect based sensor. So, till then, goodbye. Thank you.